In this video, we're looking at solving absolute value inequalities. And to start off, we're going back to two basic things that we should have already learned, and that is solving a linear inequality and solving an absolute value equation. And then we're going to put the two together and see what it looks like on the graph. So let's start off here with this example, and let's solve this inequality. Negative 2x plus 7 is less than 12. Well, to do so, I'm going to draw my line down the center, and I'm going to solve it just like a regular equation, where I'm going to subtract 7 from each side. That gives me a negative 2x is less than 5. And then I'm going to divide both sides by negative 2. And I have to be careful because whenever I divide by a negative when solving inequalities, I must flip my sign, making it greater than now. And 5 divided by negative 2 is going to give me a negative 5 halves, otherwise known as a negative 2.5. All right, and if I were to graph this on a number line, all right, and I just get some numbers on here, the main one that I need is my reference point, so I'm going to put 2 here, I'm going to put 3 here, because that would make, I'm going to put negative 3 here and negative 2 here, because that would make my negative 2.5 right in the center. All right, and you could add in some other ones to keep some equal intervals there. And what type of circle am I going to be putting? Well, I'm going to be putting an open reference point because it cannot equal, so I'm going to put that right there. And which way am I shading? Well, x is greater than, and so that's everything to this side over here, and I'd be shading that direction and get myself a nice little arrow. All right, so that's how I do a linear inequality. Let's remind ourselves about how to solve an absolute value equation. Well, once we solve an absolute value equation here, we want to get the absolute value piece all alone, isolated on one side of the equation, which I already have in this case. If there was anything else there, I would undo it by doing the opposite to get it alone. Once there, I can use the cover-up method to cover up this piece inside and ask myself, what has an absolute value of 3? And we would answer that by saying, well, both 3 and negative 3 have an absolute value of 3. So what is inside must be equal to both 3 and must be equal to both negative 3 in order to make this true. And I have two equations now that I can solve both of them just by adding 2. Finding that x could be 5, which would make this true, or x could be negative 1, which would also make this true. All right, and so I'd find that x is either 5 or negative 1, getting two solutions to this equation. All right, so those are the two things we need to start with coming in, because now we're going to put them both together, and now we have an absolute value inequality. To solve this absolute value inequality, we're going to take the same approach by doing the cover-up method on the inside. If I were to cover up what's inside of the absolute value and ask myself, what has an absolute value that is greater than 3? Well, that's any number that's bigger than 3 would have an absolute value that's greater than 3, and it's any number that would be less than negative 3, such as negative 4, negative 5, and so on. Just to prove my point, if I plug in some of those numbers, first over here, if I have the absolute value of 4, well, the absolute value of 4 is 4, and 4 is greater than 3. The absolute value of 5, well, the absolute value of 5 is 5, and 5 is greater than 3. Likewise, the absolute value of negative 4 is also 4, and therefore it's greater than 3, and the absolute value of negative 5 is also 5, which makes it greater than 3. So notice that anything that is less than negative 3 over here would make it true, and anything that is greater than positive 3 over here would make it true. So as I come back to this now, I'm going to bring back what was inside my, in this case, that's x minus 2. And I said that what's inside the absolute value, x minus 2, on this left side had to be greater than 3, which is exactly what we originally had here. All right, I just removed the absolute value bars, the sign matches, and everything else stays the same. Just like we did in the equation. One is where you just remove the absolute value bars. The second one, however, we said that what's inside the absolute value bars, x minus 2, had to be less than negative 3 in order to work. All right, notice I made everything the opposite. And in this case, everything being the opposite also included this sign. All right, our sign right there of greater than became a less than. All right, so that's what we see here. That's the difference when you're solving an absolute value inequality, is you're not just making what's on the right side of that equation the opposite, but now you're making what's on the right side of the inequality the opposite, as well as the sign itself. Everything outside the absolute value bars is becoming the opposite. From here, you just solve them both. All right, we can solve them the way that we've always done. I did not divide by a negative, so I find that x is greater than 5 in this one. And over here, I find that x is less than negative 1. All right, and I could go ahead and I can graph these on my number line. I'm just going to draw a very basic number line here. I'm going to put my 2 reference points. Negative 1 goes on the left, even though it was solved over here on the right side of my paper. That doesn't matter. Negative 1 is the smaller number, so it's on the left. And on the right there, I'm going to put my other reference point, 5. And I'm going to start graphing these. I'm going to use 2 different colors. I'll use blue for my first one here, and I'll mark this one with blue so you know. All right, it's going to be an open circle at 5, and since it's greater than, it's going this direction here. All right, and then I'm going to use yellow for my other one over here. All right, x is less than negative 1. That means it's going to be an open circle here at negative 1, and it's going this direction here. And if I notice, both of these are going to make it true. All right, and so I look at these and I could have x is greater than 5, or I could have x is less than negative 1. And it's important to recognize that this is an or, because in absolute value inequalities, you'll have an and or an or, and understanding what's going on the graph is really going to help us out here. So let's take a look. Here's our problem that we just dealt with. And what it's really asking is the absolute value graph recognized here as our V. We can see it right there, and it makes our nice V. All right. So the absolute value is greater than 3. Well, 3 is represented by this line, as we can see right here, y equals 3. So we're wondering, when will the absolute value be greater than the line? Well, let's literally take a look at the graph and see at what points is it above our line. Well, I'm just going to mark those off with yellow. This section right here is where it's above, and this section right here. Now, I don't want it to be equal to, so this would be an open circle here where it's intersecting, because it's not equal to. It's just greater than, so everything up to those intersection points. And I'm asking, what value of x is it that makes this true? Well, to recognize that, I need to look down at the x-axis. And if I trace this down to my x-axis, I see there's an open circle at the x value of negative 1, and every x value to the left of negative 1, that direction. Likewise, I come up here. If I trace this down, I see I've got an open value at an x value of 5. An open reference point, and everything to the right of that. And notice my number line that I have right here matches exactly what we were looking at right here. All right? So it's showing us that the absolute value is greater than the value of 3 when x is less than negative 1 or greater than 5. What happens if I change it now to this symbol of less than or equal to? Well, let's do it without even solving it. Let's just look at the graph and understand what's going on. Well, first off, let's look at when it's equal to 3. That's at this point right here and at this point right here. When is the absolute value less than 3? All right, well, I'm just going to come down here, and that marks the x values on our absolute value graph where the absolute value is below the line of 3. In other words, less than 3. Now, let's look at the x values that make this true. To see that, I'm going to look at the x values on the x-axis, noticing that there is a closed reference point at negative 1 and a closed reference point at positive 5. And the parts of the graph were every x value in between my 2 reference points. So I would shade this right here. And my solution would then look like this. If I just had a number line and I was just drawing it, I'd have negative 1, I'd have 5, and I'd have a closed reference point up to a closed reference point, a solid line connecting my 2 reference points there. All right, let's look at our next one here. What if the absolute value is greater than or equal to negative 1? Well, I'm going to put negative 1 in my graph here. I'm going to bring it in red. All right, negative 1 would just be, let me get myself a nice little line here. Negative 1 is just that line right there. Not entirely straight, but there we go. All right, so negative 1 is that line right there. When is the absolute value greater than that line? Well, let me just take a look at it. It's greater than here, 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 here. Oh, still greater, still greater, still greater, still greater. In fact, it's greater at every single point because it never dips below that line of negative 1. That means if I were to go draw this on my x-axis, all of these x values, both left and right, in fact, every single x value that exists would make this true. And therefore, we could say that x can be any real number, or all real numbers at this point would make this inequality true. Because the absolute value graph never is less than negative 1. It's never equal to either, but again, it didn't have to be equal to. It's just anything greater than or equal to negative 1. So we just looked at one where it was all real numbers. Now I want to challenge you to come up with one where it would be no solution. What's an inequality that you could write involving the absolute value of x minus 2 in which we could have no solution? I'm going to use the same line that we looked at last time for our all real numbers in example C, and that is y equals negative 1. And I'm going to talk about the absolute value of x minus 2's relationship to y equals negative 1. Now, we noticed that when it was greater than or equal to, it was all real numbers because it's always greater than. So what if I just flip that symbol and make it a less than symbol? All right. Will the absolute value of x minus 2 ever be less than negative 1? If I look at my graph, no, it's always greater than, and therefore this would be an example where we would find no solution because it will never be less than. And let's just look at a few other examples. You could have given anything that was less than negative, anything that was beyond 0, all right, less than 0, negative 1, negative 2, negative 3. You could use decimals, anything in there, that would have worked. And you could have done anything less than or equal to, and you could have done any decimal beyond 0, like negative 0.1, or just negative 1, negative 2, and so on. What you could not do is this, less than or equal to 0. That wouldn't be true because if we notice, 0 is our x-axis, all right, and it crosses right there. There's one solution, all right, so one solution when x equals 0. All right, and so you can't have a less than or equal to 0. That's the only restriction here, and we can't have a greater than some of those numbers. All right, and that's what we're looking at here to get a no solution. You need a less than, and you need it to be less than 0 or less than or equal to any number that was already less than 0. All right, good work if you got that. Let's take a look at a few more examples. So now it's time to try some of these on your own. See how you do. We've got a number line. Go for it. All right, come back in. Hopefully you split this into 2, where we said x plus 5 is less than 9. And over here where we kept the x plus 5, but this time we made everything else the opposite. All right, solving that, we find that we do minus 5, x is less than 4. And over here, I'm going to subtract 5. Find that x is greater than negative 14. All right, and we can come down and we can look at our reference points here. All right, and we can see that we have an open circle at negative 14, and we have an open circle at 4. And our question really at this point becomes, where am I going to shade? Last time we were shading in the middle, and the time before that we were shading on either side of these. All right, well, it all comes back to this symbol right here. All right, and we got to think about what's happening when we have an absolute value graph. Remember, our absolute value graph, when the positive form, which is what we're dealing with, is always facing upward. So if they're asking you for it to be, as we see over here, if they're asking for it to be greater than, it's going to be an or, because it's on either side of our reference points going this way and going that way. All right. If we have a less than, as we see here, it's actually going to be an and, because it's going to end up looking like this compound inequality where our shading is in between, because that's where it dips below the expected value that we're looking for. So let's come back and look at our example. In this case here, given that it is a less than, we are looking at an and situation. All right. Therefore, when I go to plot these two, I'm actually going to shade everything that is in between. It's everything in between right here. And that's what it would look like, which means that you can write your final compound probability as a compound probability with an and, where negative 14 is less than x, which is less than 4. And that would be our final statement. Let's try another one. Try this one on your own, see how you do. All right, hopefully again, you started off doing 7x plus 4 is greater than or equal to 74, where you didn't change anything. And then you did another one where you made everything the opposite. In this case, that's keeping the 7x plus 4 and making it less than or equal to negative 74. All right, and then we go ahead and solve it. We're going to subtract 4. and divide by 7. Over here, same exact steps. And in this case here, I find that x is less than or equal to negative 78/7, or you could take that down to a decimal, which would be negative 11.14. All right, if we put those reference points on our number line here, I've got a solid closed point where x is 10, so that's going to be about right here. And I have a solid closed point where x is negative 11.14. Well, I've got negative 10 right here, so negative 11.14 would be somewhere right around here. And since we're dealing with greater than, all right, we are looking at an or. And so I'm going to be putting my shading on either side of that point, going this direction or this direction, which also means when it comes to stating my answer, I must just state both of them. X is greater than or equal to 10, or x is less than or equal to negative 11.14. Let's take a look at another example. All right, try this one on your own. All right, come back in. I hope that you noticed that this time we had to subtract 10 first in order to get the absolute value of x minus 8 alone, making the absolute value of x minus 8 is greater than 12. Then at that point, we can split it off, giving me x minus 8 is greater than 12, and the opposite, where x minus 8 is less than negative 12, and then solving from there, adding 8 to both sides, giving me x is greater than 20, and over here, x is less than negative 4. Now putting those reference points on our number line, I've got an open circle at 20. All right, an open reference point there at 20, and I've got a open reference point at negative 4. And since the original one is greater than, all right, since we're looking right here, always where we solved it for that absolute value bit, I'm looking where x is greater than negative 12, so I notice I'm going to be dealing with an or statement, so these are my two answers, and my shading goes to either side of those, this way and this way. And if you really struggle to see that, you can plug this piece right here into your graphing calculator. All right, you can plug in the absolute value of x minus 8. You can put that in for y1. Remember, you're going to have to go to math and then over to num to get the absolute value, and then you put it in like that. And then in y2, you could put in 12. You will have to adjust your window, all right, so that you can actually see the line of 12, but then you could see where's the absolute value greater than 12, and you'll notice it's to either side of our reference points. Let's take a look at this last example here. Go ahead and try it on your own. All right, come back in. Again, I hope that you noticed you had to solve for the absolute value piece first by multiplying both sides by 5, giving me the absolute value of x minus 4 is less than or equal to 10. Then again, you can now split it where 1, we keep it the exact same, and 1, we make it the opposite on the other side, making it greater than or equal to negative 10. And then solving each, we find that x is less than or equal to 14. And over here, by adding 4 to both sides, we find that x is greater than or equal to negative 6. All right, that gives me my two reference points. At 14, I have a closed reference point. And at negative 6, I have a closed reference point. Noticing that my absolute value piece that I solved for right here showed that the absolute value of x minus 4 is less than 10. Where is it less than 10? That tells me that I'm dealing with an and. So that means that my shading is actually going to be between my two reference points, which also allows me to write this as a compound inequality where I've got my lower boundary, negative 6, is less than or equal to my solution region x, which is less than or equal to 14. And I can write it as one statement. All right, and that's our final one. I hope you did well. Good luck.